Welcome back to part 3 on polar coordinate systems. We're going to look at the relationships between polar and rectangular coordinate systems. Let's start with the easier method, but let's look at both methods first. To change from a polar coordinate to a rectangular coordinate, use the formulas x equals r cosine theta and y equals r sine theta. If we think about cosine theta representing how far you're going in the x direction on a unit circle, and sine theta representing how far you go in the y direction on a unit circle, then it makes sense that we would multiply the radius by the amount you are going in either the x or y direction. This will give us a distance in the x direction and a distance in the y direction, which will get us to the point that is equivalent to the polar coordinate system. The more difficult one is to change from a rectangular coordinate to a polar coordinate, but we still can do that. It just takes slightly more complicated formulas. But they're formulas you've seen already. The Pythagorean theorem, r squared equals x squared plus y squared, and tangent of theta equals y over x. Now you can think of y over x as like rise over run. Kind of gives us a slope, which can be related to the tangent line. It will even be more obvious when you get to calculus. These equations don't uniquely determine r or theta, because you do have to check to make sure you're in the correct quadrant. Let's find the rectangular coordinates of the point -4, 3 pi over 4. If we want to find x, we know that x is equal to r cosine theta, and y can be represented with r sine theta. And from here, we should probably just really quickly sketch approximately where we envision this -4, 3 pi over 4 existing, so that we have kind of this idea of where it is. If we start at the origin looking along the polar axis and we rotate 3 pi over 4, we're looking at a location angle-wise in the second quadrant. We don't go forward toward that angle, or 4, we actually back up. So we're going backwards into 4 units, 1, 2, 3, 4 units. And so our point is actually in the fourth quadrant. So when we are looking for x equals r cosine theta and y equals r sine theta, we need to keep track of the fact that it's in the fourth quadrant. Let's take a look at x. We need to find that by substituting -4 in for r, and cosine of theta, we'll substitute theta with 3 pi over 4. For r sine theta, we're going to substitute -4 in for r, and for theta, again, 3 pi over 4. That gives me a value in the x direction of -4 times -√2 over 2. And for y, we will have -4 times +√2 over 2. Now if I simplify my x coordinate, that's a negative times a negative. That gives me a +2√2 for x. And for y, I get a -2√2. Let's take a look at my picture here with the point in the fourth quadrant. If I go to the right 2, -2√2 in the y direction, it makes sense that my point in the Cartesian coordinate system is exactly the same. Now, notice that I did keep track of my signs for x and y so that I did check to make sure this worked, and it does. It does work being in the fourth quadrant. Now let's look at example 4. We're asked to find the polar coordinates of the point -1 root 3. So first I'm going to get an idea of where that point is. If I draw a point at -1 in the x direction and up approximately 1.73, so I'll just sketch this quickly as being the point that I'll be working on is somewhere right around here, which means I'm in the second quadrant where I've gone to the left 1 and up 1.73. So now I know that's what I'm going for. Now if I want to find the radius, I'll use r squared equals x squared plus y squared. And that gives me r squared is equal to -1 squared plus root 3 squared. And I will have r squared is equal to 1 plus 3. So r is equal to the square root of 4. And that's going to be a plus or minus whenever you impose a square root on both sides. And so I'll have r is equal to plus or minus 2. I'm going to just leave it awkwardly sitting there as plus or minus 2, because remember, if we have a negative radius, we can just add pi and we'll be at the same coordinate point as if we had had a positive radius. So that's just going to sit there for now. Now I need to find my angle. I'll use tangent of theta is equal to y over x, where the y value is root 3 and the x value is -1. This means that tangent of theta is equal to -root 3. And so theta is equal to the tangent inverse of -root 3. If I simplify that or find that, I'll get the angle -pi/3. Now if I were to graph -pi/3, that's going to put me down in the fourth quadrant. That's this angle down here. And if I look at how that relates to the coordinate point I'm given, I can see how there's my angle theta equals -pi/3. So remember, all I have to do is add pi and I will get the angle if I wanted to use my negative radius. So let's think about this. There are infinitely many ways to write the coordinate point. If I stand at the origin and I look out along the polar axis. Do you like how I'm using the Cartesian and the polar axis at the same time? And then I rotate down or clockwise to -pi/3. And then I back up. I back up 2 giant steps to the point -2, -pi/3. That would get me to the point I'm looking for. Now this is why it's so important to keep track of your radius, the sign of your radius, and the sign of your angle. Because I could have picked plus or minus and it would have changed my answer. So there are infinitely many ways to write this coordinate point. And you have to be mindful of which one will work out appropriately.